I am Jeremy Garafa. I'm the Sales and Marketing Director at NanoAcademic. It's a pleasure to have you today. I'm joined by my colleagues, Dr. Vincent Michaud-Rioux, today, who's going to lead the technical presentation. And we are kindly hosted by our partner, Impulse Technology, represented today by Anil and Ravikant, who host the webinar. We're going to start with a brief company presentation, NanoAcademic Technologies presentation, and then we will contextualize more the DFT technology and say more about, what is DFT, what is transport simulation, and that will make a good introduction to the NanoDCAL tool presentation just after. So, NanoAcademic Technologies, we are a Canadian company. We are located in Montreal. The company was founded in 2008 by Professor Guo and associates Dr. Zhu and Dr. Liu. We are basically a spin-off from McGill University. The company originally developed a molecular quantum transport software. NanoDCAL was the first and main tool of the company, so it's been developed for more than 10 years now. We enable the materials, science, and scientifics to predict the material properties. So that's very important, and I'm sure that in the audience we have many researchers, scientists, and engineers that do that on a daily basis. And our modeling tools are very advanced. You see here the team of NanoAcademic. So we all have technical backgrounds. Myself in micro-nanoelectronics. My colleague, Vincent Michaud-Rioux, has a strong background in atomistics and computational science. He developed some of our tools, and he's an expert in material science and physics developments for applied tools. You see, next slide, please, Vincent. And we are all experts in our fields, of course. You see here the different tools that we offer. So NanoDCAL and Rescue are the main tools we offer. Rescue is a different solver, more for physics simulation. And we will mention as well that we just released the plus versions of NanoDCAL and Rescue, the NanoDCAL Plus and Rescue Plus, which are complementary tool to the legacy tools, and they offer an enhanced modularity and a better parallelism to offer an even better user experience. Can you let the other people come into the room, please? 2 words about the market we address. Of course, we offer our tools in the entire world, and we are very happy to offer our tools to the Indian market. Our partner, Impulse Technology, offer us the possibility to address your needs. So I will mention that later, but for any inquiries, please contact Impulse Technology. So we address the academia market, the government lab market, and of course, private companies as well, R&D from startups to big companies. The license types we provide are for single users, research groups, and we have also parallel versions of our tools for HPC, for high performance computation. That's for large atom systems when you need a very large memory and strong CPU or GPU, you can have the cluster license of our tools. We provide free trial licenses as well for our products, typically 30-day free trial versions. And we continuously improve, develop, and maintain our tools. So we provide some advanced additional support. And of course, we release on a quarterly or semestrially basis our tools. Besides that, we provide expert consulting services, what we call scientific consultancy, and we can help you in your project management and develop your tool. Or additionally to the usage of our tools, we can help you in your scientific projects, such as publication of a paper and so on. Just a few words about the features and the characteristics of our tools. So our tools include many features, pretty unique features, atomistic and quantum features. We also provide QTCAD. For your information, we had a webinar last week, maybe some of you attended, about QTCAD, which is a spin qubit modeling tool. If you want to know more about it, go on our website and or on our LinkedIn page, or contact Impulse Technology for questions. We will revert to you. You will find the brochures and the leaflets of the products on our website as well. We can predict the material properties in general, all the electronic and physics properties of the materials, reduce the project time frame and accelerate the time to market, which is very important in R&D. We offer fast converging tools with advanced algorithm. We offer powerful features, so you will see the details. Vincent will present to you the details and the features of NanoDCAL in a short while. We offer efficient parallelism and a scalable design in our codes. Plenty of tutorials, so we offer an extensive documentation and tutorials for our users to get started and get proficient quickly. And to enhance the user experience, we offer friendly user interface, such as Python API in the new version, or we enable the integration of third-party solutions for plotting or display the curves and the plots, etc. For the rest, yes, notably, we offer a free 1-year service for advanced technical support. So the first year we include the technical support on our tools. And in the next slide, yes, we're gonna focus today, of course, on NanoDCAL, which is the tool that we present to you. Next slide, please, Vincent. And now we're going to present to you more context about the atomistic technology, which is always good to remind, and that will be our gateway to the NanoDCAL presentation. Thank you.
Okay, I'm going to take the mic. Thanks, everyone, and thanks, Jeremy, for the presentation. So, yeah, as Jeremy said, I'm going to start by briefly motivating why we need atomistic technology and what drove the development of our codes, and then I'll just briefly go over some overview and use cases of NanoDCAL, and then give you a little live demo of our builder. So one of the motivation for developing atomistic code was actually study the basic components of computational devices. So if we go back to like the 70s, transistors, which are the basic components, were quite large, above like the micron scale. And as time went on, like it steadily decreased, and so basically almost dividing by 2 their size every 2 years. And that is a law known as Moore's law. And why did the company follow that? Well, basically, as the performance and the material limitation limited the frequency, and you couldn't increase that much the power density in computational powers, companies that want to expand exponentially, right? You want like to grow the size of the company, the profit exponentially. Well, then the basic material that you're selling, you have to produce exponentially more of. And the simplest thing is to scale them down. So right now, in next generation fabs, companies like Intel and Samsung are basically at the few nanometer scale, and you can see that soon it's going to go pretty close to atom scale if it keeps going like that. So the more you reduce, actually, the more these devices become complicated because they display quantum effect, and of course you need atomistics because atoms start to become important. The simple addition or removal of an atom can have a drastic effect on the device performance. And so building better devices and transistors was the main motivation. Now, there's another approach to this, and it is like a more bottom-up approach, and like really from like a few atom transistor. And this idea was advanced by Mark Ratner. He's kind of a competitor and friend of our group, like he's been for so many years. And so what he proposed, like quite far back in the days, more like a theoretical idea, was to use molecules as switches for transistors. If you had that, you would already be at the atom limit. And again, you would, of course, need atomistic technology to predict the properties of these devices, understand them, and study them. So when it comes to building actual devices, you need a lot of software to help you in the creation of that. That's what we call EDA, so electronic design software. And here's like a high-level view of what a suite can look like. First, you have a process simulator telling you how the device looks, what are the materials and the various components, and how it's going to come out of the fab. Then you have like a model for your device, and you have materials. So you can use atomistic tools or other techniques that are more parametrical to simulate the materials, and then the device. And then you can extract parameters that you use in so-called compact device models to describe the devices, ideally with a few parameters, and then you put that in a circuit simulator that can allow you to predict your final chip properties and performance. So today I'm going to show tools that basically focus on device simulation and material simulation and can help you do parameter extraction. So basically the middle part of that that whole simulation procedure. So again, why do we need atomistic tools? So for simulating device, there's this plot. It's kind of arbitrary, but it shows the evolution of the number of parameter with the year of introduction. And as the devices kept shrinking, simulators that are more empirical in nature kept packing on more and more parameters to correctly describe like IV characteristics and other properties of functioning devices. So there is basically a Moore's law of parameter going along with the technology, and at some point it becomes extremely costly and not very effective to use TCAD software, which was designed to increase efficiency in the first place. So why do you need so many parameters, for example? Well, for example, as the device shrank more and more, boundary effects became quite important. So you needed extra parameters to describe the fringing field at the boundaries. As you shrink more and more, you started having more materials for electrostatic control. So that's more geometrical feature. You went from planar FETs to fin FETs, and now a gate all-around FETs, and more and more you need tons of parameters to emulate quantum mechanics and atomistics. So do we need to go through all of that? Well, we're not satisfied, so we thought that no. So back 20 years, there was a flurry of method, quantum mechanics, atomistic simulation, and combining the two, you could have accurate device modeling on somewhat small system, and that was used in science lab. And then engineering, on the other hand, had these faster empirical model, and they had data over decades. But more and more, as I show, the Moore's law of parameter basically catch up to them. And now we're at the point where basically the two meet at some intermediate scale, and powerful codes can do atomistic device modeling in useful and real-life devices. And that's where NanoDCAL comes in. And our goal is to provide quantitative prediction of carrier transport from atomistic first principle. The company, we have a vision in addition to that. So there is this pyramid of methods that's from Moraz in a VLSI technology short course. And while NanoDCAL locates here at the top of the pyramid, at Nano Academic, we also develop a drift diffusion solver, and we have an effective mass solver, and we're working on developing the center of the pyramid here. And the idea in this pyramid is that on the one side, you have more and more quantum theory that become more and more important at small scale. So you go from semi-classical to parametrical quantum theories like K.P, and then down to ab initio, where you have no parameter. And on the other side, you have continuum models that can solve pretty large device with like complex geometries that do not fit the atomic framework. And then on the other side, you have like atomistic methods. So NanoDCAL at the top of the pyramid and other codes like Rescue can be used to actually benchmark and provide parameters and parameterization for models at the lower scale. And we're building an infrastructure to have a comprehensive multi-scale transport framework. So here, the base of the pyramid is large, basically showing that you can solve larger and larger device. You could even see that as a log scale. And then on the vertical axis here, you could say that's predictive power or transferability, by which I mean the more you go up, the better you can account for device geometry, like all the materials, their electronic structure, interfaces. There's also more and more scattering effects you can account for. The atomic structure, there's all sorts of mechanism modifying the transmission and current going through these devices, so surface roughness, interfaces, there's defect phonons, and all sorts of other material properties. So let me briefly go over that, but this is just to say that in classical transport theory, you often see like basically a molecule or something with one level coupled to electrodes that way, and then you could solve some simple equations that have some parameters to describe the transport here. Now, the problem is real devices don't look so much like that as the one on the right. And then there is much more complexity here. You have like actual atoms, interfaces like gates, and of course a contact. And in general, like the simple theory is wrong. First of all, because real materials don't look like that. They have an actual density of states that come from the atomic structures, the symmetry, the atomic species, and they also have real device contacts. And if you were to account for all of that, you would need much more than 2 or 3 parameters here. You do need like an exponential number, like I showed in the slide above. And so this is all naturally taken care of by NEGF-DFT. And that was the main motivation for developing that. Okay, so I'm going to just skip to NanoDCAL. And just before I do that, let me briefly present this timeline of NEGF-DFT. So Jerry Taylor and Professor Guo published a first paper with the first like code package for NEGF-DFT, which was called at the time MEC-DCAL for the McGill device calculator. And that's very a seminal paper in the field that basically launched the whole field. In 2002, they set to do some calculations with NanoDCAL to support Ratner diodes. So these possible molecular junctions that act like transistor properties, so you can add gates and dielectric, produce IV characteristics versus bias, gate voltage, etc. And for material analysis, it comes with all analysis tool like DOS, PDOS, LDOS, projected local DOS, etc. So here shown on the right, that's the kind of structure you can build and study. So molecular bridge like this one, or more solid state interface with amorphous layer material like the one on the bottom here. Okay, other than that, yeah, Device Studio together with NanoDCAL Rescue offers you a flurry of sophisticated approach to study your materials. You can build interfaces, heterostructure, layered materials, devices, and you can then compute and analyze results in all the various ways that are necessary. Are we limited in what we can do? Yeah, here's an example of all kinds of things you can do with some reference. You may take a screenshot if you like. So like molecule absorbed on graphene surfaces, molecular devices. You can compute semiconductor surface reconstruction. I believe that's a 5x5 or 7x7 silicon surface here. You can calculate the effect of photons incident on devices combined with some bias. I'm going to show an example of that. Complex materials, interfaces, layered carbon-based materials, etc. So here's again some shots from Device Studio. So you can like build, redefine crystals, and there's a user-friendly interface to set up all sorts of calculator, going from total energy to DOS, allowing you to perform some smart analysis on your results and your calculations. Here's a use case of NanoDCAL. So the study of spintronics. So spintronics is one of the forthcoming next generation nanoelectronics. It has low power consumption because spin dissipate very little heat compared to electrons. You could then reach much higher density and have increased performance. But one of the principal issue there is a principle to achieve a large spin polarization in these devices. Graphene nanoribbons have intrinsic edge magnetism, and so they have been put forward as a natural platform for spintronics. But there's really tons of principles for creating so-called spin currents. So here, I want to talk about this paper by Shishi Tao and ally. And so in this device, it's based on carbon nanogriffin encapsulated in boron nitride. So the edge atom of the graphene in this system have magnetic moment like 0.3 boron magneton. By comparison, the nickel atom at room temperature has a magnetic moment of about 1.3 boron magneton. So that's quite a significant magnetic moment. And here on the right, the top figure is the band structure of the suspended graphene nanoribbon. And because the spin up and spin down bands are degenerate, although the spins are separated in real space, you cannot really address the spin. So put a bias on this device, you're going to send all the spins one way or the other, and they basically cancel each other. However, if you encapsulate this graphene nanoribbon in graphene, because of the two sublattices that BN create, you're going to split the degeneracy of the band around the Fermi level. And so one of the gap is 0.28 eV, and the other one is 0.82 eV. And what can you do with that? Well, then you can think that optically, because you have a direct band gap here, you could activate the spin of just one of these channels by shining photon on it. So that's the proposal here. So if you shine photon, you're going to excite, let's say, just spin up states because you tune its energy to activate just those states. So then you have, conducting electron of only one spin, but then they don't necessarily go anywhere. But what you can do with NanoDCAL, because it's a transport code, is then add a bias to this device and see how the electrons would start moving from one electrode to the other. So if you do that, it's been shown you can tune also the bias voltage and calculate the transmission and everything. And by choosing a bias voltage slightly smaller than the gap, let's say 0.25, you can get a significant pure spin current, and you're guaranteed that all the electrons flowing from one side to the other are going to be the single spin type. Going back to my first slides, another thing you can study with NanoDCAL, for example, as reported in this paper by Alina and Sareva, is a molecular junction. So in this paper, NanoDCAL is used to study the transport in the graphene material, gamma graphene, deposited on silicon 111 surfaces. So graphene have been under theoretical study since the 1990s. And gamma graphene is one of, I think, the 4 most common phases of graphene. And you can see the band structure on the right is reminiscent of that of graphene, except that it has no direct cone, and at gamma and M, you have a actually like a quadratic band near the maximum, and it has a direct band gap of about 0.5 eV at the endpoint. Now, this has been synthesized on some surfaces, copper surfaces, in 2010. And unlike graphene, for example, this material has small corrugation, so you don't drastically modify its electronic properties and structural integrity by putting it on a silicon surface. So here that's proposed as a good substrate. The lattice mismatch for the scale of devices we're talking about is relatively small, under 4%. And the absorption energy per atom is calculated at minus 430 milli eV. So there is some good structural integrity here. And plus, with NanoDCAL, it was possible to compute the calculating some density difference. You can represent and see in various planes what is the bonding between the graphene and the silicon surface. And this is, as one might expect, covalently bonded. So I'm going to accelerate just a bit here. So you can study atomistically what happens if you put like perfect structure together and how that modifies the dust. Then you can relax the whole thing and look at this transmission plot, and at various places calculate the scattering state. So like here around 0, you can see a good hybridization of the scattering state, which is shared by everything in between the graphene and the substrate. You can then use, for example, Device Studio to etch some trenches like here and calculate the transport properties again. So in the paper, the authors etch about 10, 25, and 50 nanometers of substrate under the graphene, and then recalculated the transport properties for all these junctions, which includes hundreds of atoms. So that's a very large calculation, but thanks to NanoDCAL's efficiency, this is not a problem. And then some counterintuitive result maybe is that because of quantum interference, you don't necessarily have linear behavior in the etching of these devices, and there's basically some kind of periodicity in how much the current can pass, and so there is more transmission in the 50 angstrom bridge than in the 25 bridge, for example. And lastly, the author looked at what happens if you put some bias voltage on these bridges or a gate. And basically, what is maybe peculiar compared to other devices, like semiconducting devices, is here. You can actually turn the device on and off by putting a bias voltage instead of just a gate voltage. So at basically low bias, this thing would be conducting, and the stronger the bias, the lower the transmission around the Fermi energy here. Okay, so I'm going to switch to the live demo part of the webinar. Okay, so here I have the Device Studio interface. So you can see it has like a few buttons. And what I will build is a molecular junction where two gold molecules contact the alkanithiol molecule. And I'll show you how to do various kind of analysis calculation along the way. So the first step of the project is maybe like creating a new project like that. So let me just do untitled here. And then you can easily import either from online in some material database or from a local database some material. So I'm going to import some gold. You have a good database of material. I'm going to go in 3D, conductor, pure metal, and select gold. So here I have just a single gold atom. So I want to create a lead. So I'm going to first go to a face-centered conventional cell like that, so I can preview it and then build it. And then I'm again going to create some tips for the contact, and so I'm going to use a supercell of that, which is 2 by 2, and give it some thickness. And then I'm going to carve a tip out of that. I'm going to start with that. I can go in the XY plane, remove some atoms like that, and go back to my XY view. And then you can see the bonds here, maybe. I'm going to select these atoms, consider this one. And here I have this tip here. The next thing is I want to create some more vacuum around this tip, because now this is a little bit too tight. It might interact with itself. So I'm going to come here and add some vacuum and then build. Now, because I like symmetry, I'm going to center that along the A and B vectors. So it can be done here. Center along A and B. And now I have my tip here. All right. Now the next thing I want to do is import the molecule I want to deal with. So I'm going to take a new molecule. Oh, I don't want to build it. I want to import it. Going back to materials, the organic materials, I'm going to import this alkanithiol molecule that looks like that. So I'm going to make a copy of that just to save my work. Oops. And then I want to reflect that tip to the other side to create two tips to contact my molecule. So how do I do that? I can use this button to mirror all the atoms. I'm going to do that across the XY plane. And here, I've pre-calculated from the relaxed structure, but you could do that independently that I need a bridge about this length. So if I apply that, now I have my extra tip here. And I'm going to need to extend this unit cell to have the right length. So and copy this like that, such that this atom is equidistant with this atom, and the lattice is basically periodic. So now I have this bridge. The last thing I got to do is take those atoms, and I'm doing Control C here, and Control V here. And then this thing is going to appear beside, and I can select the atoms and center everything so that it will be at the bridge where I want it. Then you can you could do a full relaxation of the structure. So I've done that in advance because it takes a few minutes, and I don't want to do that here. And then you could like analyze the structure, look at the bond length here, the bond length here. If you don't want it, you can clear these annotation. You can look at the angles. Now here we still have a periodic structure. So to create a device, it's very simple. You just go in the build tools, click convert to device, and then you can tell it what kind of electrode you want. So you can add up to 6 electrodes here. Here I want left and right electrodes. It's going to automatically pick up the lattice constant from the gold. You can preview to see if that's correct. Or that's correct. If it's not, you can do that by hand if your device is super complicated, and then you build. And there you have your molecular junction. Now let's take a few steps back. The first thing would be to analyze my lead. So that's basically bulk gold. I could look at here in the simulators. There's many simulators, but you see Rescue, NanoScale, and NanoDCAL, all codes developed at Nano Academic. And then I can do like a self-consistent calculation. You can adjust the electron temperature, the energy cutoff, so that's for the how much the grids are fine, and you can adjust the key sampling. Iteration controls, that's for the mixing methods and the convergence of the self-consistent cycle. You can determine the basis set. You're going to figure out by default that you want to use LDA, and it doubles it at polarized basis. And then you can add some spin if you like. Gold is not spin polarized, so I'm just going to generate the files. Finally, it's going to automatically write a script like that you could fix, or you could add some more parameters if you're an expert user of NanoDCAL. And then you can just click run, and this is going to compute the self-consistent density. Once you're done, you can click analysis. There's all sorts of analysis tool. You could put in the density of state here. Again, just the key sampling. Maybe you want to go higher. You can compute the projected density of state. You can add a band structure calculator. Select the path here. So you have the Brouillon zone. You can select your points. By default, it's going to go around it. You can add charge analysis, the electron density. You can decide what kind of charge you want. You want a neutral atom charge, total electron, etc. And then just click generate files. I've pre-computed that in some other place. So I'm just going to briefly show you after. I just want to show you for the device. You similarly compute, open this SCF calculation for devices. You can adjust the K-sampling. Here I would go 111 because this thing is not periodic. Now you have contour integration. That's for the green function integration description. You can adjust the temperature in the electrodes. That's important if you want to compute, let's say, thermal transport. So you may have temperature gradient between the electrodes. Again, basis, set, spin, iteration control. And then you can generate the files. So it's going to create a structure like that where you can run the electrodes and the device. And then you will see some other kind of analysis here. Now you can compute things like IV curve, thermoelectric current, photocurrent, and more. Now let me just load this project. So here I've just pre-calculated for gold. So once I've done these calculations, all of these files, I can do something like show view. It's going to show the band structure here. You can slide it around, look at some points. You can look at the electron density. Oops, my window stuff. Electron density, you can look at how the density distributes as an iso surface around the atom. And for the device, you can look at the transmission. So not much peak around the Fermi energy here, and you can see what's the gap, and you can integrate the current here. And in this example, you can also calculate the local density of state and take some line cuts across the central device and see, I think that's the Fermi energy. What's the local density of state in the device. Lastly, like I showed in the previous paper, you can also compute the density, say, for a gold tip, and then for the molecule and the full junction, and then you can get the subtract these two from this one and get the total energy difference. Here this curve value is not well adjusted, but if you go at, let's say, 0.1, you will see that this difference shows that most of the charge redistribution happens between the sulfur atom here and the tip, and so that indicates that there is some significant bonding happening in this region of the device. All right. So yeah, that completes my demonstration and what I wanted to demonstrate. There's just a quick list of the topic here, and I think at this point we'll just move into the Q&A section of the talk.
Yeah, thank you. Thank you very much, Vincent, for this complete presentation and live demo that gives a very good oversight and insights of NanoDCAL. We're going to move on to the Q&A session now. Anil, with your authorization, to go till the 8 p.m. mark on your end, maybe we could spill a few more minutes to take questions from the audience. And there are a few more information maybe to communicate to the audience today. But we can definitely start taking questions. Please start preparing your questions. And there are a few more things that Anil will and I will discuss with Vincent inputs as well.
Hello, Dr. Vincent. Can you hear me?
Yeah.
Hi. Thank you. Thank you for the nice presentation. However, one thing is not clear to me during the live demo. Is there any inbuilt database in the NanoDCAL software, database of materials?
There's a database of atomic species inside NanoDCAL, and there's a database of materials that is part of Device Studio. And for example, the gold and the molecules are imported from the database of Device Studio.
So yes, Hemanta, Anil here. I would like to explain. Yes, database is there for all molecules, one-dimensional material, two-dimensional material, insulator, conductor, all materials database is there. Even apart from that database, we have an integration with the material project open source database. So through API, you can also import the material from online open source library.
Okay, that's great. One more thing I would like to ask, is there any web page where you have provided any tutorials for the starters to do some playing with the tool?
Yeah, there's an extensive tutorial that has been written by one of our distributor in Chinese, and it's translated with Google Doc, but now we are doing a proper translation of the documentation. There's also tutorials for like NanoDCAL alone, if you'd like to use as a standalone tool.
Excuse me, I am Vincent.
Yeah.
Thank you. Yeah, for the very nice presentation. I have one doubt regarding the kind of functionals and about the basis sets you are using.
Yeah, so as for the basis sets, we have various general purpose and special purpose double zeta polarized bases. There's a few single zeta polarized or triple zeta polarized for some elements, and NanoDCAL has a tool to regenerate and optimize bases with given some metric.
Okay, another issue is regarding kinds of gate materials we can use. You have shown we can apply voltage, but we can use different kinds of split gate kind of arrangements.
So it's possible to, so that the gate material is basically specified by the dielectric constant. So you can use an effective solvent gate if you like. If you'd like a real atomistic gate, then you put the atoms, and it's going to cost more computational time, but you'll get the full interaction.
Okay, finally, the kind of computational resources needed to run standard simulations.
So for this simple device I showed, you could use just a single core of your laptop, and to do everything, it's going to take a few minutes. And but if you have like very large devices, like the one I showed in the presentation, so many hundred of atom molecular bridge, then you probably need like a workstation to do that, maybe with 60 cores or something of that order.
Okay, thank you.
Thank you, Vincent Matthews, for the question. We're going to take Eamon's Aurora questions, please.
Sir, actually, I want to ask that in this software, can we use the other approximation, like you have showed the LD approximation in that? Can we use hybrid and GGA and semi-empirical like things in that?
Yeah, you can use various LDA GGA approximation. There's some meta GGA implemented in there. There's also methods to modify the element like VCA. There's no hybrid functional support implemented, but that is a feature of Rescue, where we have a special algorithm to compute non-local operators in periodic systems.
Okay, sir. And what is the maximum amount of atoms we can use in that? The number of atoms?
Yeah, with NanoDCAL, the limitation is mostly from the memory. But yeah, it's been used in I think the largest calculations reported in the literature are around 5,000-6,000 atoms.
Okay, sir. Thank you.
Thank you. Vincent, we have a question in the chat from Dr. Vimala. Is there any example available on your website for field effect transistor device implementations? If yes, please share. I don't think we have that at the moment, but it's something that we may have in a near future. Is it something that you can talk briefly about, the FET device in NanoDCAL?
Yeah, in NanoDCAL and Device Studio, it's possible to well, let me briefly show. There is a where is it? Simulator. It's part of the analysis. So you can build a transistor here and specify, for example, the number of gates and if there is a dielectric and in what region. Yeah, there's a tutorial showing how to do that. It's also one of the first things we put in the NanoDCAL Plus documentation. So yeah, if you're interested, you can reach out to us and I can send you the link after that.
Thank you, Vincent, for this precision. Dr. Vimara, is it okay? If you have any more questions, please, yes, thank you to you. If you have some more technical questions, please reach out to Impulse Technology and they will follow up with your questions. Vincent, if you can show the last slide of the presentation to conclude. In the meantime, if there are some other questions, we have some more minutes to take.
Yes, sir. I have a question, sir. I have a question.
Okay, go ahead, please.
Sir, actually, I just wanted to know, using this NanoDCAL, is it possible to know the defects of the structure, like nanostructure, like graphene?
Yes, you can study defects. There's, yes, I can briefly show there. There's actually tools to build, for example, nanotubes, nanoribbons. You can build a simple sheet like that. And then we create a supercell, say like that. Oops, it's the wrong axis. A little bit off, but whoops, I just have my axis messed up, but let me just create that. And then you can use a selection tool, select an atom, and then just replace it by, let's say, a nitrogen atom. You could do the calculation and then study the charge around there and the charge density difference.
Okay.
Also relax the structure. And yeah, for sure, this kind of material analysis is part of the tool.
Okay, sir. Thank you, sir. Thank you.
You're welcome. Thank you too for your question. So if there are no more questions, and you can still ask while I conclude. So thank you very much to Impulse Technology for hosting this webinar today. Thank you very much to Vincent for the technical presentation, demo, and responses to the audience questions. Don't hesitate to follow Impulse and Nano Academic on LinkedIn. We publish articles, we publish news on a regular basis. We're gonna go live with our new website, Nano Academic new website in the coming days. So there will be more content and more information on our tools, especially NanoDCAL, but not only. And for your information, as we said, we freshly released NanoDCAL Plus and Rescue Plus beginning of January. So if you are interested in those tools, please reach out to Impulse, and we will gladly follow up with you. And again, for NanoDCAL or Rescue questions, anything about our atomistic tools, please reach out, and we will be happy to answer.
So
thank you for your time. Yeah, a question maybe?
No. Myself.
Yeah, go ahead, Anil.
Yeah. So now I would like to thanks all the participants and our principal who has beautifully given this nice presentation and live demo. So I request to the participants, if you have any queries, kindly drop an email, or you can directly call on my cell number, which is showing on the display. So don't hesitate, contact to us. We will have a more discussions. If any questions is pending, then we can have a 1-to-1 discussions with you and your teams, so that we can fully technically satisfy with the related to any of these products from Nano Academic Technology. So once again, thank you to joining.